Hey, I'm Stephen and this is Solving the Money Problem. If you're new, welcome. If you're not, welcome back. So, Andrej Karpathy, who I think his official title at Tesla is the Big Daddy of Artificial Intelligence and Autopilot Vision, recently did a talk at the Scaled Machine Learning Conference 2020. I'm going to run through a few clips in this video and just add a few comments here and there. Alright, without further ado, let's dive in. Hey guys, before I forget, WeBull have extended their offer for US residents. If you'd like to help out the channel and get up to 2 free stocks, use the link in the description. Alright, let's get back to it.
Globally, we now have roughly 1 million cars. And for the purposes of the team, these are not just cars, these are computers. They're internet accessible, and we can both deploy over-the-air updates to them and get a lot of data from them that helps us develop the autopilot. And they're also robots, so they have sensing, they have actuation, and we're developing the brains of that computer. Now, the most basic kind of autopilot functionality is that when you turn it on in your car, the car will keep its lane and it will keep distance away from the vehicle ahead of you. We've now sort of accumulated almost 3 billion miles on the autopilot, which sounds like a lot.
This is a really important point. I really just want to emphasize this because Andre is not going to necessarily linger on something that seems so obvious when he's speaking to a crowd of people that understand deep learning and data and artificial intelligence. But the thing here is Tesla's fleet of over 1 million vehicles now is out there. It's collecting data. It's alive. And the thing is that everyone else who's attempting to solve full self-driving does not have the fleet. They cannot collect the volume of real world data. They cannot go, oh, hang on, we're having problems with this particular task. Can we access a lot of cases on that and then solve this particular part of it? No. Tesla is the only company that has the fleet collecting the data. Data is how this will be won. I really wanted to stress this at the start of the video so it's not overlooked. It's so important.
Now, you're seeing here, for example, A/B pedestrian is 5.6 out of 6 points. I think these numbers are kind of slightly abstract. So let me actually put that in context. Really, what are we talking about here? Pedestrian A/B is the following. Here's one example. The car just, someone just emerges from in between parked cars. And this car may not have even been on the autopilot, but we continuously monitor the environment around us. We saw that there's a person in front, and we slam on the brakes automatically. Here's another example. Looks like a pretty benign scene. This person is probably not paying attention. The pedestrian is not paying attention. We slam on the brakes and prevent a collision.
Looks like a few nominees for a Darwin Award there. Goodness me. Wow. Anyway, let's carry on. It's good that these automatic safety features are able to detect and save people from exiting the gene pool, even if that seemed to be their wish.
Here's one more example. You can see the trouble coming from the right. It's really hard to tell because everything is occluded, and then suddenly there's a pedestrian. We slam on the brakes and avoid a collision again. So 5.6 out of 6 is kind of abstract, but we see a lot of these. We see tens to hundreds of these per day.
Again, just take a moment to let the implications of that settle into your mind. Hundreds of these examples of cases of people running out in front of vehicles every single day, helping to improve and train the AI to get better at that exact scenario.
Here's a WayMo. I just took a small clip. A WayMo comes to an intersection and takes a left through the intersection. You've seen this for a decade. So how is this special? Why are we so late? What's taking so long? And it looks the same. So I think the critical point to make is that it looks the same, but under the hood, it's completely different in terms of the approach that we take towards full self-driving. So in particular, we take a heavily vision-based approach. So everyone else has a LiDAR on the top of the car. The LiDAR shoots out lasers and creates a LiDAR kind of point cloud map. And then you pre-map the environment that you're going to drive. So you have a high-definition LiDAR map, and you localize to it to a centimeter-level accuracy. And then you know exactly the path you're going to take, so you can just steer to keep yourself perfectly localized in the correct region. So this is quite helpful, but this is not the approach that we take. We do not have LiDAR on our cars, so we don't shoot out lasers. It's all camera-based. And we do not build high-definition maps. So when we come to an intersection, we encounter it basically for the first time. We come to an intersection. How many lanes are there? Left, right, center? Which way should I turn? What are the traffic lights? Which lanes do they control? All of this is just done just from camera vision alone. And so this is a bit of a harder problem, but of course, once we actually get this to work, we can also deploy it to the millions of cars that we have globally.
This may not sound like a particularly important point, but believe me, it is. The difference between using LiDAR and a vision-based system to solve full self-driving is just night and day. Why? Look, we have a great example of a computer and a camera-based system, our eyes and our brain, being able to do a pretty good job of driving vehicles. So we know vision is a path that can work. Using LiDAR is almost like trying to teach somebody to see by taping their eyes shut and then giving them a blind person's cane and saying, oh cool, you can just bump your little cane around and poke things, and you'll realize if there's an obstacle there and you won't walk into it. But it's not solving the vision problem, is it? LiDAR is effectively like just shooting out lasers going, how far are things around me? And it doesn't know anything. It's not building a picture. It's not actually solving the vision problem, which is how we as human beings drive vehicles pretty successfully, not perfectly, of course. So I think that this is a distinction that really needs to be emphasized. Tesla is about the only company that's going down the vision path. And as Elon Musk has said, everyone using LiDAR is doomed. I mean,
so for stop sign detection, as an example, we have a approximate detector for stop signs based on an initial seed set of data, and we run that and deploy that to cars in shadow mode. And then you can detect some kind of a lack of health of that detector at test time. So for example, the stop sign detection is flickering. That could be a source of uncertainty. You can also detect that the neural network is uncertain in a certain Bayesian way, and there's a few ways to model that. You can find instances where you get surprised to see a stop sign, like why didn't you see it when you were a bit further away? You can also source examples when we detect a stop sign, but the map thinks that there should be no stop sign, or vice versa. So sort of a map vision disagreement. So we have lots of different ways of sourcing difficult cases, and then we upload images, and we look through them, we label some of them, and incorporate them into a training set.
I mean, I hate to harp on about this again, but only Tesla can do this because only Tesla has a fleet of its size, and only Tesla can pull that number of examples and solve specific cases that can go, oh, okay, we're having issues detecting, it's got some uncertainty, okay, cool, let's pull a ton of examples and solve this problem. No one else can do it. They don't have the fleet. GG.
As an example, we've struggled with these heavily occluded stop signs. We found that the detector was not performing very well when they were heavily occluded. And that we have a mechanism in this data engine process where we can actually train these kinds of detectors offline. So we can train a small detector that detects an occluded stop sign by trees. And then what we do with that detector is that we can beam it down to the fleet, and we can ask the fleet, please apply this detector on top of everything else you're doing. And if this detector scores high, then please send us an image. And then the fleet responds with a somewhat noisy set, but they boost the amount of examples we have of stop signs that are occluded. And maybe 10% of them are actual occluded stop signs that we get from that stream. And this requires no firmware upgrade. This is completely dynamic and can just be done by the team extremely quickly. Is the bread and butter of how we actually get any of these tasks to work. It's just accumulating these large data sets in the full tail of that distribution. So we have tens of thousands of occluded stop signs. The fleet can send us as many as it takes. We have the biggest data set for except right turn on stops. I'm basically certain of that. We again create a detector for this, and then we get a noisy stream from the fleet of cars encountering except right turn on stops, and then we can label that, incorporate into a training set. We have tens of thousands of these. I'm not actually 100% sure how you build out a data set like this without the fleet.
Now look, I may be hallucinating here, but I've got a bit of a feeling that Andrej might be a bit of a low-key savage, and that might have been a bit of a jab at the other companies attempting to solve full self-driving, maybe inferring there, if you guys don't have the fleet, you're f***ed. I don't know, let me know in the comments. Do you think that maybe there was a second meaning to that, or it's just a very innocent comment, just talking about data in general and AI and machine learning and how very important it is to have a large fleet to solve this problem? Let me know.
I'm not actually 100% sure how you build out a data set like this without the fleet. So the North Star for actually achieving this for us is called Operation Vacation, which I'll describe in a second. But basically, the idea is that for any new task, you have a latency to actually the task working. And there's a process, and we understand how to the process for getting a task to work. And we're trying to develop as much automation machinery to actually support the development of these new features and new tasks. And we're removing engineers from that loop so they're not involved. We're just building out infrastructure, and then we have a data labeling team and PMs and so on that can actually use that infrastructure to create new detectors. So as an example, we're working with caution lights recently. We're trying to detect when the police car lights are turned on. This is an example of a new task that we'd like to know about. And we sort of have a cookie cutter. We know exactly what to kind of approach to. We know exactly what it takes to get a task to work. All the infrastructure is in place. So this task, we're going to treat it as a landmark task. Landmark is an example of a prototype. So we have a detection prototype, a segmentation prototype, a landmark prototype. And these are just classes of tasks. And if your new task is a member of any of these, or an instance of any of these prototype classes, then all of the infrastructure is just plug and play and goes through the full data engine. You can collect the seed data set, you label your examples, you source more examples in the cases where you're failing, you deploy it to in shadow mode, you source examples, and you grind up metrics, you create all the unit test predicates. All this is completely automated. And this we're mostly developing the automation infrastructure, and then it's easy to develop any new task, and that's kind of how we get this to work.
So not only does Tesla have the data, which nobody else has, but because of that, they're able to innovate and develop new ways of actually automating the process of improving the self-driving AI. No one's got the data, therefore no one's even been able to develop these same techniques. This is like watching Usain Bolt race a bunch of 3-year-old children. And on top of that, literally removing engineers from the process who other companies are having to pay to do these tasks, WayMo, etc. They're going to find other new places for these engineers to apply their brains, right? And we know Tesla's got some of the best engineers in the world.
So what I've explained so far is you take an image from one of the cameras, you run it through this shared backbone, and you make lots of predictions about it in the image pixel space. So we can potentially predict objects, lines, or edges, and so on. Taking the example of edges, where does this go afterwards, right? So here's a video, and I'm showing the predictions of the road edge task on all of the different cameras. And you can see that this is basically a binary segmentation problem for us. And we detect those edges here, and we use this to wind our way through a parking lot because we'd like to go to a certain destination but avoid all the road edges. Now, you can't just drive on the raw predictions of these edges in these two-dimensional pixel pixel coordinate systems. So a lot of our networks have been moving towards these bird's eye view network predictions, where you take all these cameras and you feed them through backbones, and then you have neural net fusion layer that stitches up the feature maps across the different views and also does the projection from image space to bird's eye view. And then we have a temporal module, potentially, that actually smooths out these predictions. And this is all neural net components. And then we have a BevNet decoder that actually creates the top-down space. And so then we can directly, potentially, predict these road edges in a top-down view. Now, this makes a huge difference in practice. So here's an example. In top row, I'm showing the left camera, center, right. And I'm showing road edge detections in red. On the bottom row, on the left, you see the ground truth of what this intersection looks like. And you see that the car is positioned on the dot. And so that's the ground truth. On the very right, you see what happens when you take 2D predictions in the images and you cast them out. You basically get garbage. Like, it somewhat works around the car. There, the projection is easy. But far away, especially near the horizon line, a few pixels of error means lots of meters of error. And so these projection-based techniques are extremely hard to get to work. You'd have to know extremely accurate depth per pixel to do that projection. It's a very hard problem. And in the middle, you are seeing some of our predictions from the recent bird's eye view networks that just kind of make these predictions in top-down view directly. So let me show you a video here of what this looks like in practice. On the top, we will have a video of an intersection. On the bottom, I'm showing some of the predictions achieved by the Tesla AI team that has produced these bird's eye view networks. We have road edges in red. We have dividers in green on the very left. Then we have attributes for these dividers. So we want to know if it's an actual curb or if it's just like a logical curb, so like a yellow line or something like that. And then we have a traffic flow direction and a few other things like that. I'm only showing some examples. But the car is on the bottom center of these images. And as we're turning through this intersection, these bird's eye view networks just predict pretty far away the full structure of this intersection and what it looks like. So this is extremely powerful for us.
It really is pretty amazing to see that stuff being sort of painted into a bird's eye view landscape of the environment that's constructed just from all of the cameras surrounding the vehicle, just using 2D vision. But what's really more fascinating to me is the fact that this system is working so much like a brain. Look, I'm a nerd. I've read a ton of books on the brain. Neuroscience is a really fascinating subject for me. And what I'm noticing is a bunch of parallels between the way that a human brain works and categorizes objects, for example, like hard edges and stuff like that. I don't know if you know, but they've got a layer of meaning and hierarchy that's sort of happening in our brain at any point in time. We don't just see a bunch of colors and stuff coming in. We see that's a hard edge, that's an object, that's animate, that's a human, that's an animal, that's foliage, that's a tree, okay? So we have this way of automatically deciding this is something else, etc., And so the vehicle is learning the same things. It's detecting objects and categorizing things in the exact same kind of a manner that we're doing. And also, what's even more important, we make predictions about what we think we're seeing when we're driving forward too. Have you ever, if you've driven a vehicle at any point, thought you had seen an extra lane where there wasn't one or something along those lines, and partway through an intersection or something you've realized that your prediction was incorrect and what you thought was there was actually wrong? We're seeing this same system of prediction now being built up, and we're seeing the visual representations, those red lines, the edges and stuff. This is so close, and there's so many parallels between the way that our vision system and our brain work and the self-driving AI system that Tesla's developing, that it's hard to not see them solving this at such a general level that they're going to be the ones that everybody's wanting to buy the self-driving software from in the future, because it's the only one that works. Everything else is like a baby with training wheels, taking the wrong approach, it's blindfolded or something. So we'll see how this plays out, but this is just one great example that you can see exactly what is being inferred by this system and the way that it's functioning so much like a human brain and how it's understanding its environment.
Here's an example of using this for objects. So on the top, we have our camera feeds. On the middle, I'm showing our per pixel depth predictions achieved via self-supervised learning. We need those depth predictions because we take, as many others do in the literature right now, we take a pseudo LiDAR approach where you basically predict the depth for every single pixel, and you can cast out your pixels, and you basically simulate LiDAR input that way, but it's purely from vision. And then you can use a lot of techniques that have been developed also for LiDAR processing to actually achieve 3D object detection.
Just if anyone's watching and a little bit confused about that depth perception, basically what you're saying is black means it's very far away and white means it's basically on top of you, and then we've got a spectrum of color in between. So the brighter and lighter something is, the closer it is. So you'll see that as objects are coming towards the vehicle, its depth perception is making them brighter, and as they're going further away, they're darker.
So on the bottom, you have then predictions of our detector directly in the bird's eye view. Here I have one more slide showing just our depth predictions for some other videos. This is not very exotic for any of you who are in computer vision, because there are entire workshops on creating videos like these where we are basically achieving depth directly from images. And this is done, of course, no human can annotate depth. So this is done using self-supervised techniques. So in particular, we take an image, we predict a depth. Then when you have a depth for an image, you can cast out all the pixels into 3D, and you can reproject them either into camera views at that same time, but different cameras, or you can reproject them into the future frames of that single camera. And then you have a photometric loss that's enforcing consistency. And so the only way to predict, to make everything consistent in reprojections is to predict the correct depth. And so this learns in a self-supervised fashion to predict depth, and then we can simulate LiDAR inputs directly from vision and use this downstream to make these bird's eye view predictions. And as you might be familiar, the gap is quickly closing in state-of-the-art approaches. If you give yourself LiDAR and how well you can do, versus if you do not have LiDAR, but you just use vision techniques and use pseudo-LiDAR approaches, and that gap is quickly shrinking in academia. And we see a lot of this as well internally.
Translation: Tesla, without any of the expensive butt-ass ugly LiDAR hardware, is able to infer depth almost as accurately today as LiDAR, and they're improving.
In particular, we have huge data sets of people driving cars. So when people drive cars and they steer the wheel, they're actually data labeling for you. They're showing you how to drive through any intersection or any other kind of place.
I've mentioned this in other videos, but it bears repeating. It's literally like Tesla customers pay Tesla for the privilege of getting a vehicle out on the roads that will collect data to send back to Tesla to improve the self-driving AI. It's nutty. They've got millions of people. Instead of having engineers they're having to pay like a six-figure salary to drive around, collect data, all that kind of stuff, their own customers who are paying them, buying vehicles and making a profit for Tesla along the way are paying for the privilege of it. It's nuts. Here's a quick response from Andre to an audience question about using maps data.
So we do collect maps, we just don't collect high definition maps. Like when a WayMo or something like that is driving through an environment, they know that the leaf on that tree is 15.53 meters away, like to centimeter level accuracy. We don't know about the leaf of that tree, but we do know that there's a stop sign somewhere in the vicinity here. And so we do build low definition maps where we do map stop signs, traffic lights, and things like that, because it provides a second layer. Yeah. And then also that helps us, again, like I mentioned, it helps us with all the trigger infrastructure for sourcing examples, because we can look for discrepancies between map and vision, and that's a really good signal for us for getting lots of more images of really tricky cases.
I really do recommend everyone watch the full talk. There's a link in the description. If you're a Tesla investor, you're curious about the company, or you're interested in AI or self-driving technology, it's really worthwhile to see where Tesla's at. And in my personal opinion, maybe I'm biased as a Tesla investor, it seems pretty clear to me that Tesla has an unassailable lead. I believe that the people going down the path of LiDAR, which is almost everyone, is fucked. It's a dead end, okay? It's not that difficult to infer that a vision-based system. When was the last time you banged your head by walking into an object? It doesn't happen that often, does it? Because with our vision system and our computer, we can infer depth. We can use the same solution for autonomous driving. There's no arguing with that. The second thing is that people that aren't going down the LiDAR path, they need the data. Where are they going to get the data from? Please, somebody in the comments, explain to me, how does anyone catch Tesla now, okay? 3 billion miles driven? How? Here's how I see things playing out. Tesla solves full self-driving first. Tesla gets regulatory approval first. Everyone else is completely screwed and hasn't managed to solve the problem. And now they're faced with the choice. Do we continue to put vehicles on the road which we know will result in more people dying? Or do we swallow our pride and go, hey Tesla, what's up dude? You know what? Can we get some of that self-driving software that you guys figured out because you're smarter than us? Yeah, well, let's just license that from you. This is what I personally see happening. Look, if I'm wrong, I'm fine with that. I would really hope that lots of other people can solve the same problem. And one of the points that's really easy to overlook is how Tesla is automating this entire process. Not only do they have an unassailable lead, they are automating that acceleration of their progress, okay? Holy crap, it's just, there's leverage upon leverage, advantage upon advantage. It's good. I'm sorry, but it is game over. From where I'm standing, I don't see anyone catching Tesla on full self-driving. But hey, if you have a differing opinion, please let me know why I'm wrong in the comments. I'm Stephen Mark Ryan, this is Solving the Money Problem, and I love you all.
Thanks so much for watching. Let me know your thoughts in the comments below. Do you agree or disagree with any points? And of course, if you have any ideas for future videos, let me know. I read all your comments. P.S. If you're still watching, you're awesome. This channel has kind of blown up since it launched, and I'm working on making the best possible content for you guys, but it takes time. Consider supporting the channel at patreon.com/solvingthemoneyproblem so I can continue creating content for you guys. There's a link in the description. And you can now also become a member of the channel to get some exclusive perks. To learn more, click the join button next to subscribe. Either way, the best form of support is you being here and watching, so thanks again.